What's the derivative of the inverse sine of x, or arcsine of x? We're going to be using implicit differentiation for this, so if you haven't a clue what that is, you might want to go learn it. As they usually come in pairs, we are also inadvertently figuring out the derivative of the inverse cosine of x too, and I'll show the working for both. Before anything, we're going to need to know two things: the derivatives of the regular functions themselves, and the basic trig identities. Don't worry, because I'll be showing them later on when they're needed anyway. Now, with y equals arcsine of x, our goal is to find its derivative dy dx. First, let's take sine on both sides, giving us sine of y equals to x. From here, we're going to be using implicit differentiation. We'll start with the right side. Derivative of x with respect to x, no brainer, it's 1. On the left, we're going to take the derivative of sine y with respect to y multiplied by the derivative of y with respect to x. I'll explain why this is done in case anyone's confused. This is the part of the video where I publicly shame you for not listening when I told you to go learn implicit differentiation beforehand. Let's say we have g, which is a function of y, and y is a function of x. In order to find the derivative of g with respect to x, dg dx, we need to take the derivative of the g function with respect to y multiplied by the derivative of the y function with respect to x. This gives us dg dy times dy dx, and you'll see that the dy terms cancel out, leaving us with dg dx. So when the g function is something like sine of y, we have to take the derivative of sine of y with respect to y and then multiply it by dy dx. This is actually the chain rule at work. And so, with that, we get the derivative of sine of y with respect to y, that being cosine of y, multiplied by the derivative of y with respect to x, dy dx, which is what we were looking for from the start. Rearranging to find for dy dx, we find that it's equal to 1 over cosine of y. From here, it wouldn't really be ideal to just sub y equals arcsine x back into the equation, because we get cosine of arcsine, which, like your mother, ain't pretty. Obligatory JK? You might be tempted to turn 1 over cosine into secant, but that doesn't look good either. Secant of arcsine wouldn't be fun to evaluate. Instead, we'll use the identity sine squared plus cosine squared equals 1. We simply find cosine in terms of sine, so we can plug in our arcsine value later. With dy dx now equal to 1 over square root of 1 minus sine squared y, we plug in our y function to get dy dx equals to 1 over square root of 1 minus sine squared of arcsine x. Just a quick in-between, but sine squared of arcsine x can be written as sine of arcsine of x, whole thing squared. Sine of arcsine x is just x, so we're left with x squared. Finally, we get dy dx equals to 1 over square root of 1 minus x squared. Thus, the derivative of arcsine of x is just that. Now, in the beginning, I said that we can also find the derivative of arccos by similarities. So I'll show it quickly. When y equals arccos of x, take cosine on both sides and implicitly differentiate. Derivative of cosine y is negative sine y, so dy dx equals negative 1 over sine y. Based on the identity, we find for sine in terms of cosine, so we can match with the initial function y equals arccos x. Then, plug in y into cos squared y just like we did with sine. Therefore, dy dx equals negative 1 over square root of 1 minus x squared. And you'll notice that the derivative of arccos x is just the negative of the derivative of arcsine x. This pattern remains true for all the derivatives of inverse trig functions and their cofunctions. I'll probably cover the rest in another video, and once again, if you have any other ideas, do let me know.